Let me share with you something that I found particularly weird when I was a student first learning calculus. Let's say that you have a circle with radius 5 centered at the origin of the xy plane. This is something defined with the equation x squared plus y squared equals 5 squared. That is, all of the points on the circle are a distance 5 from the origin as encapsulated by the Pythagorean theorem, where the sum of the squares of the two legs on this triangle equal the square of the hypotenuse, 5 squared. And suppose that you want to find the slope of a tangent line to the circle, maybe at the point xy equals 3, 4. Now, if you're savvy with geometry, you might already know that this tangent line is perpendicular to the radius touching it at that point. But let's say you don't already know that. Or maybe you want a technique that generalizes to curves other than just circles. As with other problems about the slopes of tangent lines to curves, the key thought here is to zoom in close enough that the curve basically looks just like its own tangent line, and then ask about a tiny step along that curve. The y component of that little step is what you might call dy, and the x component is a little dx. So the slope that we want is the rise over run, dy divided by dx. But unlike other tangent slope problems in calculus, this curve is not the graph of a function. So we can't just take a simple derivative, asking about the size of some tiny nudge to the output of a function caused by some tiny nudge to the input. X is not an input, and y is not an output. They're both just interdependent values related by some equation. This is what's called an implicit curve. It's just the set of all points, xy, that satisfies some property written in terms of the two variables, x and y. The procedure for how you actually find dy dx for curves like this is the thing that I found very weird as a calculus student. You take the derivative of both sides like this. For x squared, you write 2x times dx, and similarly y squared becomes 2y times dy. And then the derivative of that constant 5 squared on the right is just 0. Now, you can see why this feels a little strange, right? What does it mean to take the derivative of an expression that has multiple variables in it? And why is it that we're tacking on the little dy and the little dx in this way? But if you just blindly move forward with what you get, you can rearrange this equation and find an expression for dy divided by dx, which in this case comes out to be negative x divided by y. So, at the point with coordinates xy equals 3, 4, that slope would be negative 3 divided by 4, evidently. This strange process is called implicit differentiation. And don't worry, I have an explanation for how you can interpret taking a derivative of an expression with two variables like this. But first, I want to set aside this particular problem and show how it's connected to a different type of calculus problem, something called a related rates problem. Imagine a 5-meter long ladder held up against a wall where the top of the ladder starts 4 meters above the ground, which by the Pythagorean theorem means that that bottom is 3 meters away from the wall. And let's say it's slipping down in such a way that the top of the ladder is dropping at a rate of 1 meter per second. The question is, in that initial moment, what's the rate at which the bottom of the ladder is moving away from the wall? It's interesting, right? That distance from the bottom of the ladder to the wall is 100% determined by the distance from the top of the ladder to the floor. So we should have enough information to figure out how the rates of change for each of those values actually depend on each other. But it might not be entirely clear how exactly you relate those two. First things first, it's always nice to give names to the quantities that we care about. So let's label that distance from the top of the ladder to the ground y of t, written as a function of time because it's changing. Likewise, label the distance between the bottom of the ladder and the wall x of t. The key equation that relates these terms is the Pythagorean theorem. X of t squared plus y of t squared equals 5 squared. What makes that a powerful equation to use is that it's true at all points of time. Now, one way that you could solve this would be to isolate x of t, and then you figure out what y of t has to be based on that 1 meter per second drop rate, and you could take the derivative of the resulting function, dx dt, the rate at which x is changing with respect to time. And that's fine. It involves a couple layers of using the chain rule, and it'll definitely work for you. But I want to show a different way that you can think about the same problem. This left-hand side of the equation is a function of time, right? It just so happens to equal a constant, meaning the value evidently doesn't change while time passes, but it's still written as an expression dependent on time, which means we can manipulate it like any other function that has t as an input. In particular, we can take a derivative of this left-hand side, which is a way of saying, if I let a little bit of time pass, some small dt, which causes y to slightly decrease and x to slightly increase, how much does this expression change? On the one hand, we know that that derivative should be 0, since the expression is a constant, and constants don't care about your tiny nudges in time, they just remain unchanged. But on the other hand, what do you get when you compute this derivative? Well, the derivative of x of t squared is 2 times x of t times the derivative of x. That's the chain rule that I talked about last video. 2x dx represents the size of a change to x squared caused by some change to x, and then we're dividing out by dt. Likewise, the rate at which y of t squared is changing is 2 times y of t times the derivative of y. Now, evidently, this whole expression must be 0, and that's an equivalent way of saying that x squared plus y squared must not change while the latter moves. At the very start, time t equals 0, the height y of t is 4 meters, and that distance x of t is 3 meters. And since the top of the ladder is dropping at a rate of 1 meter per second, that derivative dy dt is negative 1 meters per second. Now, this gives us enough information to isolate the derivative, dx dt. And when you work it out, it comes out to be 4/3 meters per second. The reason I bring up this latter problem is that I want you to compare it to the problem of finding the slope of a tangent line to the circle. In both cases, we had the equation x squared plus y squared equals 5 squared, and in both cases, we ended up taking the derivative of each side of this expression. But for the latter question, these expressions were functions of time, so taking the derivative has a clear meaning. It's the rate at which the expression changes as time changes. But what makes the circle situation strange is that rather than saying that a small amount of time dt has passed, which causes x and y to change, the derivative just has these tiny nudges dx and dy just floating free, not tied to some other common variable, like time. Let me show you a nice way to think about this. Let's give this expression x squared plus y squared a name, maybe s. S is essentially a function of two variables. It takes every point xy on the plane and associates it with a number. For points on this circle, that number happens to be 25. If you stepped off the circle away from the center, that value would be bigger. For other points xy closer to the origin, that value would be smaller. Now, what it means to take a derivative of this expression, a derivative of s, is to consider a tiny change to both of these variables, some tiny change dx to x and some tiny change dy to y. And not necessarily one that keeps you on the circle, by the way. It's just any tiny step in any direction of the xy plane. And from there, you ask, how much does the value of s change? And that difference, the difference in the value of s before the nudge and after the nudge, is what I'm writing as ds. For example, in this picture, we're starting off at a point where x equals 3 and where y equals 4. And let's just say that that step I drew has dx at negative 0.02 and dy at negative 0.01. Then the decrease in s, the amount that x squared plus y squared changes over that step, would be about 2 times 3 times negative 0.02 plus 2 times 4 times negative 0.01. That's what this derivative expression, 2x dx plus 2y dy, actually means. It's a recipe for telling you how much the value x squared plus y squared changes as determined by the point xy where you start and the tiny step dx dy that you take. And as with all things derivative, this is only an approximation, but it's one that gets truer and truer for smaller and smaller choices of dx and dy. The key point here is that when you restrict yourself to steps along the circle, you're essentially saying you want to ensure that this value of s doesn't change. It starts at a value of 25, and you want to keep it at a value of 25. That is, ds should be 0. So setting the expression 2x dx plus 2y dy equal to 0 is the condition under which one of these tiny steps actually stays on the circle. Again, this is only an approximation. Speaking more precisely, that condition is what keeps you on the tangent line of the circle, not the circle itself. But for tiny enough steps, those are essentially the same thing. As a final example here, I want to show you how you can actually use this technique of implicit differentiation to figure out new derivative formulas. I've mentioned that the derivative of e to the x is itself. But what about the derivative of its inverse function, the natural log of x? Well, the graph of the natural log of x can be thought of as an implicit curve. It's all of the points xy on the plane where y happens to equal ln of x. It just happens to be the case that the x's and the y's of this equation aren't as intermingled as they were in our other examples. The slope of this graph, dy divided by dx, should be the derivative of ln of x, right? Well, to find that, first rearrange this equation, y equals ln of x, to be e to the y equals x. This is exactly what the natural log of x means. It's saying e to the what equals x. Since we know the derivative of e to the y, we can take the derivative of both sides here, effectively asking how a tiny step with components dx, dy changes the value of each one of these sides. To ensure that a step stays on the curve, the change to this left side of the equation, which is e to the y times dy, must equal the change to the right side, which in this case is just dx. Rearranging, that means that dy divided by dx, the slope of our graph, equals 1 divided by e to the y. And when we're on the curve, e to the y is, by definition, the same thing as x. So evidently, this slope is 1 divided by x. And of course, an expression for the slope of a graph of a function, written in terms of x like this, is the derivative of that function. So evidently, the derivative of ln of x is 1 divided by x. By the way, all of this is a little sneak peek into multivariable calculus, where you consider functions that have multiple inputs and how they change as you tweak those multiple inputs. The key, as always, is to have a clear image in your head of what tiny nudges are at play and how exactly they depend on each other.